So this will be lecture number 2, and we'll pick up where we left off last time, discussing the size scale of membrane processes. So the use of membrane technologies to perform separations often breaks down upon or along the lines of the size of the components that are being filtered out of a medium, be it gas or liquid, by the membrane. And it goes all the way from literally molecular separation, separating ions from water, or separating molecular mixtures of gases that where the species that are being separated are on the order of just a very few angstroms and may differ only in size by fractions of an angstrom, all the way up through conventional filtration, where one might be trying to remove large particulate matter from water streams, for example. And in between, in the microfiltration and ultrafiltration region, these are porous membranes that are very effective for removing, for example, viruses and other organisms that can be toxic to humans. And so these technologies are used significantly for water purification. Very typically, membrane processes are operated using a driving force, and for things like gas separation and reverse osmosis, this is typically a hydrostatic pressure gradient. For other separations that we'll talk about later, like pervaporation, a difference in chemical activity can be applied without changing pressure. Likewise, for things like dialysis, it's a changing concentration species of interest that drives the mass transfer, and we'll develop models to help us understand and predict the performance of in each of these types of applications. I've had a long interest in the history of science in this field, and as I indicated in class earlier, we go back to antiquity, to, for example, Aristotle, who noted that if salt water were evaporated, that it would become sweet, or would be freed from ions. And much later, we now do this on very large scale with reverse osmosis membranes. And so I thought it would be interesting to walk through some of the early history of membrane science, and just to give you a flavor of some of the initial studies, the kinds of membranes they were using. You can see glimpses of the scientific methodologies that were being applied, and I think it's also just really interesting. And so the first recorded example that we know of for permeability comes from Jean-Antoine Nollet, the Abbé Nollet in France. And so although he was trained in theology, he was a scientist working in the church, and at that time a lot of the educated people were in the church, and so a lot of the science got done in the church. And this is a drawing from the original article by the Abbé Nollet of the device that he was using in his experiments. And I'll take just a very short detour to draw your attention to the Journal of Membrane Science, volume 100. When the Journal of Membrane Science started with volume 1 and then volume 2 and so forth, it was not at all clear that the scientific community needed or wanted a Journal of Membrane Science, nor how long the Journal of Membrane Science would last as a viable and profitable journal for Elsevier. And so when the Journal of Membrane Science made it all the way to volume 100, there was a special celebration to mark this this point, and the editors of the of the journal went back through time and collected what were regarded as a set of the most influential papers in membrane science up to that time, so from the beginning of history back up through 1995. And they reproduced these articles, in some cases like Fick's article. They were translated from other languages, and this one, for example, I believe was also translated from French. And they're in a really convenient way to just see how some of the key events in membrane science, in the discovery phase of membrane science, took place. And this is certainly one of them, the first recorded example of membrane permeability. And so at this time, there were no synthetic membranes. All of the membranes were naturally occurring. They'd be things like natural gum that would come out of rubber trees, so what we would use today to make rubber balloons could be formed into membranes. Various animal body parts. Antoine Nollet is using a bladder from a pig, and that was a common membrane used in a number of early studies. And so what he has done is he has placed in this central glass cylindrical tube, he's placed ethanol under vacuum and purged it from air, and then he's tied a pig bladder over the top of it to fasten it, and he has made it as tight as he possibly could. And then he plunged this device into a vase that has water in it. And he says he came back after 5 or 6 hours and was surprised to see that now the cylinder had more liquid in it than it had at immersion. And even though he had filled it right to the rim, the pig bladder that was used to cover the flask had become convex and had stretched so much that when he pricked it with a pin, the jet of liquid spurted out, rising to more than a foot in height. And so there's the wording for this, and this is a crude diagram of what he saw. So he originally put the spirits of wine or ethanol into a vial, covered it with this pigskin bladder, and put that in water, and went away for several hours and was surprised to see that pigskin bladder distended in this fashion. And he goes on to speculate that he was certain that this could only have occurred because the introduction of water into this flask had caused the pig bladder to rise, as shown in this right-hand picture. And then he did another experiment to test that hypothesis, and so you see the scientific method being played out here. And in the other experiment, he put water inside this cylinder, covered it with a pigskin bladder, and then immersed it in a bath of ethanol, and he saw the opposite behavior. That is, that the pig bladder gradually sank into the flask, and the volume of water appeared to be reduced. And so he goes on to write that he did not know yet what force was acting on the water caused it to enter the flask, but whatever it was, it had to be considerable to overcome the difficulty of transmitting through the pig bladder, and also had to be strong enough to actually overcome the mechanical properties, the resilience of the membrane, and bend it either in this way or in this way, depending on whichever way the experiment was operated. And so what has happened here is this pigskin bladder is more permeable to water than to ethanol. So this is an example of semi-permeability. It's the guiding principle behind which we use membranes for separations today. And as a result of this, in this first setup of the experiment, the water can enter the vial where the alcohol is faster than the alcohol can get out. There is a concentration gradient, high concentration of water in the vase, low concentration in the cylinder, and that drives the transport of water across this pigskin bladder or membrane, and that's faster than the driving force for ethanol to leave. And so we now step forward a good bit and leave the liquid side of the experiments and focus on John Mitchell, who's an American physician, and work with gases. And so Mitchell was teaching at the Philadelphia Medical Institute and had an interest in understanding, was studying gases and their use in medicine. And so his story starts that he read a paper. This would be like giving a conference paper before the Philosophical Society, of a new method of forming gum elastic into thin plate sheets and bags. And so gum elastic would be natural rubber. It would come out of a rubber tree, and he was reporting how to form it into various objects. Now, bags here you might read as balloons, and what he found was that if he took these balloons and filled them with hydrogen, then and sealed them, then the balloon would ascend to a considerable height in the atmosphere, and then after some time would descend after a period of time. And he didn't understand why the balloons would come back down. That is, once they're filled with hydrogen gas, and hydrogen being lighter than air, that would cause the balloons to rise. But what would make them come back down? It was not clear. And so here again you see the scientific method coming in. And so he's postulating the gas might have escaped from the balloons at the ligature. That's where he had the balloon tied off or sealed. Could have permeated through the dense wall of the balloon material, or could have chemically combined with the internal surface of the rubber balloon. And so he did a series of experiments to run through these hypotheses to see what was going on. So he first took a section of his balloon and put it over a wide mouth bottle and tied it so that it was sealed. He had put hydrogen in it, and in a few hours the cover descended into the cavity of the bottle. That is, if you have this bottle that's sitting out in air and it's filled with hydrogen, and at the mouth or top of the bottle is a thin membrane of essentially what we would call today natural rubber, and the hydrogen will diffuse or permeate across that membrane faster than air gases can permeate in the opposite direction, and as a result, then the membrane descends into the cover of the cavity of the bottle, and it went all the way to the point where the cover was burst inwards by the pressure of the atmosphere. And he weighed his membrane and found no weight gain, and so presumed that the hydrogen must have escaped by some mechanism. And so here's an example of his experiment with hydrogen inside his jar with the rubber membrane covering it, air on the outside, and over a period of time he would see this membrane start to sink into the jar, finally to the point where it would rupture. And he then went on to do another experiment, and that is, if the hydrogen has come out, where did it go? the hydrogen has come out of here, where did it go? So he did another experiment now where he put a bell jar over this apparatus and let the experiment go again, and again saw the membrane collapse down into this hydrogen filled jar, and he noted that the air now above this jar became an explosive mixture. He didn't say exactly how he tested that, but we take his word for it. And the contents of the bottle itself remained to be essentially pure hydrogen. And so he was surprised that the hydrogen could penetrate its way through the membrane to get out into the air when there's no pressure difference applied. And he said it must be by some inherent power of considerable amount. And he found that the facility of permeation was much greater in the hydrogen than in atmospheric air, and because he found almost no air inside this bottle. And so hydrogen is just way more permeable through this natural rubber membrane than air gases are. And so, seeking to understand this further, he reversed the experiment like the Abbé Nollet did. So put air inside the bottle and have a bell jar that has hydrogen around it, and then the hydrogen enters the bottle and causes the membrane now to stretch in the opposite direction, formed into a globe, and finally burst. And so he hypothesized that the minuteness of the atom of hydrogen, the small size of hydrogen, might account for the greater facility with which it went into this membrane. But it didn't describe, that alone didn't explain the energy or the driving force for which this occurred, which we now would know would be a chemical potential or partial pressure gradient. And he went on to examine the rate of transmission of other gases through these natural rubber balloons. And he found that ammonia would transmit through these balloons in 1 minute as much as volume as H2S did in 2.5 minutes, and so on and so forth. And this is the beginnings of understanding that these rubber balloons could in fact have a permeation of gases at different rates, and this then ultimately became the basis of large-scale use of polymer membranes for gas separations many years later. And if you come forward now and look at permeability, which is a measure of how rapidly gas molecules can transmit through a membrane at steady state, and we'll go into more details about that a bit later. But essentially, for many polymers like polydimethyl siloxane or silicone rubber, you see that nitrogen has the lowest permeability of all of the gases considered. And this was what Mitchell had observed as well, that nitrogen was the slowest gas to permeate through these membranes. Now we'll learn that that's because of the relatively large size of nitrogen, which makes it slow to diffuse, and also its relatively low solubility in many polymers. And so both of those factors combine to make hydrogen slower moving through polymer membranes than virtually any other gas that one might use among the simpler gases. This is just background information on Mitchell's experiments, so we will skip through that. Some of the terminology for the way he refers to chemicals are not in common use today, so I put this up so you'd know more or less what he's talking about. And here's the last couple we'll look at. Now, when he goes out to publish his work, and this is also in volume 100 of the JMS, is reproduced there at least. So he has published this work, and he takes a crack at Sir Thomas Graham, whom we'll come to in a moment, who's a giant in the field of the early days of membrane permeation experiments. And I don't know how many of you have had a chance to write peer-reviewed articles for the scientific literature, but normally it's a fairly courteous process nowadays, and we don't take shots at our colleagues or folks who may be reviewing our papers or grant proposals and so forth. But this doesn't appear to have always been the case, and so he's talking about work that Graham has done, and he expresses his surprise at the failure of Graham to investigate a principle based upon an unusual result that had, according to Mitchell, had been placed conspicuously before him. And he goes on to rail a little bit about the ancient methods of research and how they needed to be abandoned in order to advance nature and truth. And I just thought that this was a striking example of something that might have been read over many hundreds of years in various aspects of science, and wanted to share it with you. And so the next historical figure that we'll come to is Adolf Fick, and he published the Phenomenological Laws of Diffusion in 1855. He was a physiologist and worked basically as someone who studied anatomy of cadavers at a medical school. And he was not always slated to work in the sciences or the natural sciences, and it was his brother who got him into medicine and into more of the natural sciences. This is a bit about when some of his early years, and he postulated what we now know as Fick's laws when he was just 26 years old, and it came from the concept that that Fourier's theory of heat transfer and Ohm's law of conductivity, electrical conductivity, could be extended to describe the laws of mass transfer. He also constructed one of the first successful models of a contact lens, and now this is made of glass and not some very high permeability polymer, but so he was active in the medical field and also in basic science through this his work as a physicist. And so this is Fick's work. It was published twice, once in English and also in the original German. And it's also in volume 100 of the Journal of Membrane Science. And it starts out that a few years ago, Graham, and that's the same Sir Thomas Graham, published an extensive investigation on the diffusion of salts in water, in which he especially compared the diffusibility of different salts. And here in red comes another little tweak of Graham. It appears to me to be a matter of regret, however, that in such an exceedingly valuable and extensive investigation, the development of a fundamental law was neglected, and I have therefore endeavored to supply this omission. Okay, and Fick goes on to postulate that it was quite natural, perhaps quite natural to Fick, to suppose that this law for diffusion of a salt in its solvent must be identical to that according to which the diffusion of heat in a conducting body takes place. Upon this law, Fourier founded his celebrated theory of heat, and is the same principle which Ohm applied to such extraordinary success in electricity. And so at 26 years old, looking at data from Sir Thomas Graham about the diffusion of salt through water across a glass frit, or a membrane, if you will, it's natural to Fick to suppose that the governing physical principle is similar to diffusion of heat in a conducting body or diffusion of electricity in a conductor. And he went on then to formulate what we would now know as Fick's first and second law. And he says, accordingly, the transfer of salt and water occurring per unit time between two elements of space filled with differently concentrated solutions must be directly proportional to the difference in concentration and inversely proportional to the distance of the elements from one another. That is, that the change, the flux of salt and water moving through a mixture where the salt concentration is different in one place than it is in another, that had to be proportional to the difference in concentration of salt between these two locations and inversely proportional to the distance between them. And he formulated this in a form that you can recognize if you look at only the first term on the left-hand side and the first term on the right-hand side and replace these squiggly deltas with partial derivatives, and K is what we would now call the diffusion coefficient, and this gives exactly the so-called Fick's second law of diffusion, the flux law, that the flux would be proportional to the to minus K times the concentration gradient falls out of that as well. And so at the bottom of this page you see the equation that we would now refer to as Fick's second law. Okay, that's it for this set of notes, and we'll go ahead now and pick up the next set of them. And now we've been talking for a while about the players that are shown here, and the last one I'll speak about in this section is Sir Thomas Graham. And so you've seen a number of the earlier authors refer to Sir Thomas Graham, and now want to share with you a bit about some of his remarkable contributions to the early days of permeation. And he was studying the transport of salts through water. That was what had sparked Fick's interest in his work. But he was also studying the movement of gases through natural rubber membranes. And upon his studies, he postulated the movement, or the basic mechanism by which gases transport through polymers, and he said that it occurs via condensation of the gas at one surface, diffusion of the gas through the polymer, and evaporation to a gaseous state on the other side. And this is today known as the solution diffusion mechanism, and now well over a century and a half later, this mechanism is the fundamental backbone behind which we understand the transport of small molecules through all types of non-porous polymer and polymer composite materials. He also made a number of other very important observations that turn out to be absolutely correct, including that these natural rubber membranes can be used to separate gases. This is just a little bit of his background. You can see here some indication that he got some pushback from his family about career choice, and ultimately wound up studying at Glasgow University and working in chemistry, and eventually took up a chair of chemistry in a university in the UK in 1830. There's some note that he was reported not to be a really good lecturer, and I just provide that to provide a little more human touch for Graham. But he was absolutely a genius in the laboratory, and made enormous contributions there, even though he might not be so good at teaching elementary university classes. So this is from an article that's again in the volume 100 of the Journal of Membrane Science, Notice of a Singular Inflation of a Bladder. And it talks about a bladder now is a balloon made out of natural rubber. And he took a sound bladder, that means it doesn't have defects or pinholes or anything, and filled it about 2/3 with methane, and then valved it off, and put it into a bell jar. So you can imagine having a balloon that has methane in it, and you put a bell jar around it that is filled with carbon dioxide. Now, we know today that carbon dioxide transmits through polymers always much faster than methane. CO2 is a smaller molecule and it has much higher solubility, and so this is another case that harkens back to the Abe-Nolais experiments and some of Mitchell's experiments. Because what he found was that after about 12 hours, instead of this partially inflated balloon with methane in it, the bladder or the balloon was found to be distended to the utmost and at the very point of bursting. And most of the CO2 in the receiver had disappeared. And when he tried to take his balloon out of this device, it actually burst at the neck. Those of you who are involved in experimental research can feel his pain now, I'm sure. And it was found that he found that inside his balloon or his bladder, which had mainly methane to start with, he found in the end it had 35 parts by volume of carbon dioxide. There's no carbon dioxide, or almost no carbon dioxide in that balloon at the beginning. And he investigated his balloon material, seemed to be quite fresh to the smell, and appeared to have undergone no change. On the other hand, the CO2 that remained in the bell jar had acquired very little of the methane or the coal gas. And the conclusion is unavoidable that the closed bladder or sealed balloon was inflated by the insinuation or the permeation of carbon dioxide gas from outside. That is, the CO2 would permeate into this balloon faster than the methane would permeate out. And so the balloon would actually inflate itself. Now, Rahul and I are going to do an experiment for you in which we will use something a little less flammable, but we will reproduce in part Sir Thomas Graham's article. And the way we'll do that is to take natural rubber balloons. These are the kind that you might buy at a convenience store and inflate for a birthday party, just run-of-the-mill rubber balloons. And we'll inflate one of them with oxygen and the other with nitrogen. And what we will notice is that the balloon that is inflated with oxygen over a period of hours and days will gradually shrink, and it will become instead of being taut originally, it will shrink down in size and become flaccid. On the other hand, the balloon that has nitrogen in it will initially grow, and over periods of a couple weeks it will gradually and slowly increase its size. And we'll show later that this is occurring because every polymer, including the rubber balloons you would buy at a convenience store, are more permeable to oxygen than they are to carbon dioxide. And so if you have a balloon that is filled with nitrogen, there is a driving force for oxygen to permeate from the outside air, where the oxygen content is 21%, into the balloon where there's no oxygen initially. There's also a driving force for the nitrogen to permeate from inside the balloon out, but because nitrogen is very slow, the oxygen will permeate into that balloon before the nitrogen can permeate out, and overall the balloon will grow. With oxygen, the situation is totally reversed. The oxygen comes out of the balloon faster than the nitrogen can come in, and the balloon overall deflates. But this was must have been a strange observation the first time that one would see it. And he went on in another paper to postulate what's now known as the solution diffusion mechanism, which is the backbone behind which bedrock theory upon which transport in non-porous membranes is based. And it starts out with work from Mitchell. And Dr. Mitchell discovered a power of gases to penetrate rubber balloons in thin sheets. And these, he found then that he postulated that gases undergo liquefaction when absorbed by liquids and such colloidal substances as India rubber. So it's known that gases, when they dissolve in liquids, they take on a density of the, or they exist in an environment that's a liquid-like density. And so he's postulating here that gases dissolve, that condense and liquefy essentially when they dissolve into a material such as India rubber. And this is the solubility step in the solution diffusion model. And their transmission through these materials is then affected by agency of the liquid and not gaseous diffusion. In other words, that the diffusion coefficients that govern gas transmission through polymers are not gas phase diffusion coefficients, but they're diffusion coefficients that are applicable for these condensed media like liquids and solids. The rubber is then wetted by these liquefied gases, and on the downstream or low concentration or low partial pressure side, the gas evaporates into a vacuum and reappears as gas on the other side. So this is the first statement of what's called the solution diffusion mechanism for gas transport through polymers. And again, that's become the backbone for how we understand and describe gas transport through polymers today, and also things like water and ion transport through reverse osmosis desalination membranes. So we'll spend more time quantitatively with this a bit later. So this is the structure of natural rubber. Today you'll find it on things like all your automobile tires have cis polyisoprene or natural rubber like this. And so this is the material that Graham and Mitchell and so forth were making their membranes out of. This is an example of a slide illustrating the solution diffusion model for polymers. And it shows a membrane, a non-porous membrane, for example, a rubber membrane or a polysulfone membrane in a gas separation application in contact with a high pressure of a gas mixture on the left-hand side, and a low pressure on the downstream side. And as a result of this pressure difference, a concentration gradient in the gas is established inside the polymer, and that concentration gradient drives diffusion by Fickian diffusion. And the first step in this process is the sorption or the dissolution of the gas into the polymer at the upstream or high pressure face. The second step is the diffusion down the partial pressure or chemical potential gradient, and the third step is the desorption from the downstream side. And in all of the polymer membranes we know of today, this middle step, the diffusion down the partial pressure gradient, is the rate limiting step in gas transport across such a polymer. And the rate limiting step in that diffusion is the slow segmental dynamics of the polymer chains that I showed you with the brief movie of hydrogen diffusing through polysulfone. The polymer chains are moving slowly, and their random thermal motion gives rise to local gaps in the polymer matrix through which the gas molecules can execute diffusion steps. And so depending upon how far apart the polymer chains are or how rapidly they move, you can change diffusion coefficients by orders of magnitude. And this is one of the ways that people change transport properties and separation properties of materials for gas separations, is by changing the backbone structure of a polymer in order to either make it more or less flexible and to make it more or less dense. Those factors have enormous impact on rates of transport. We normally write the steady state flux of a gas, J sub A, in the following form, where P sub A here is the permeability coefficient, and the lowercase p's are the partial pressures of gas A on the feed side of the membrane and on the permeate side of the membrane, and L is the membrane thickness. That is that the flux goes up as the thickness goes down, and so today modern desalination membranes are of the order of 50 nanometers thick, and modern gas separation membranes will be on the order of 50 to 100 nanometers thick, because the thinner you make the membrane, the higher is the flux for a given permeability and a given pressure difference. The permeability, if you turn this around a bit, can be viewed as the flux of gas properly normalized for thickness and for driving force. So it's essentially a pressure and thickness normalized flux, and is typically taken to be a material property. That is, it depends on the material or on the polymer. It'll also depend upon the gas, because every polymer has a different permeability coefficient for each gas, and for a given gas it'll have a different permeability coefficient in every polymer. Within the context of the solution diffusion model, we can write the permeability coefficient as a product of the diffusion coefficient of the gas through the polymer times the solubility coefficient of the gas in the polymer. And so one way of looking at this, or understanding this concept, is that the permeability is essentially the pressure and thickness normalized flux. How much gas can you get through the membrane? And that depends upon how soluble the gas is in the membrane, how many molecules of gas can you dissolve in the membrane, times how fast they diffuse or how fast they move through the membrane. So the rate at which you can get molecules through the membrane depends upon how likely they are to dissolve in the membrane, and then how fast they move through the membrane once they're dissolved. Now, we're often interested in gas transport through membranes, sometimes for barrier applications where you just want to keep everything, every gas from going through, but often we're interested in using these membranes to separate gas mixture. And so we want materials that are not only permeable to one component, but that they have the ability to be more permeable to that component than to another. And we quantify that characteristic as the so-called selectivity, and it's the ratio of the permeability coefficients of two gases in a polymer. So P sub A would be, for example, the permeation of oxygen through a silicone rubber membrane, and P sub B would be the permeation of nitrogen, or P sub A would be the permeation of hydrogen through that membrane, and P sub B would be the permeability of methane through that membrane. So it's a ratio of two permeabilities in the same material is a measure or a yardstick of how effective that material is at separating those two gases. Within the context of the solution diffusion model, P is equal to D times S, we can write the selectivity in terms of a ratio of the diffusion coefficients of the two gases and the ratio of the solubility coefficients. And so the way we can manipulate or fix selectivity or change it is by changing the relative diffusion coefficients of the components, the gases in the polymer. We do that by changing the backbone chemistry that changes the open space in the polymer or changes the molecular motion of the polymer, or by putting chemical groups on the polymer that either act to enhance or retard the solubility of one component over another. And so these are coming back to some of Graham's work. He also noted that there was a tendency for gases to penetrate most readily in rubbery polymers, that is, in these natural rubber materials he was working with, like rubber balloons, that the gases penetrate most readily, which are most condensable and most soluble in liquids. And he went back to the work of Mitchell, where Mitchell noted that different gases had transmitted at different rates through the same membrane. And Graham noted that it will be observed that Mitchell's results that those gases penetrate most readily, which are easily liquefied by pressure, and which are also generally highly soluble in water or other liquids. And so this is a plot of the solubility of gases in polydimethyl siloxane, silicone rubber. And the solubility of a gas in a polymer is expressed in much the same way as a solubility of a gas in a liquid is expressed. And so it's expressed in units of cc's of gas at standard temperature and pressure. And remember that there are 22,400 cc's of gas at standard temperature and pressure in a mole of gas. So this is really another way of writing moles of gas per cc of polymer per atmosphere. And so if you want to calculate the concentration of gas in the polymer, you multiply the solubility times the pressure of gas that's in contact with the polymer. So this is a bit like might be called a Henry's law constant in gas solubility in liquids. And it turns out that there's very, very general trends that gases that have very low tendency to condense, as judged in this case by their critical temperature, tend to have very low solubility. And as the critical temperature increases, gas solubility goes up by more than an order of magnitude. Now these are solubility results for one particular polymer and a few gases. If you were to take other polymers and make similar measurements, they would line up perfectly parallel to the line that's shown here. If we were to go to handbooks and look up the solubility of these gases in water or in hexane or benzene, they would also line up perfectly parallel to this line. And so this is a general tendency that's observed across many classes of many polymers and many classes of materials. Now, you can replace the critical temperature here with some other measure of the tendency of penetrant to condense. So there are cases where people will use the normal boiling point for gases that have a normal boiling point and see very strong correlations. The gas that has the higher normal boiling point has a higher solubility. Delta, the enthalpy change on vaporization, can be used as the x-axis for this plot and get very strong correlations with solubility. Gases that have large delta H of vaporization tend to be highly soluble in liquids. And so this is something that we see ubiquitously almost in gas solubility in polymers, and Graham had observed it well over a century ago. And in materials like polydimethyl siloxane, there's often a reasonable trend in the overall permeability or the net rate of transport of gas with critical temperature or tendency to condense. And this is what Graham was getting at. It will be observed that those gases penetrate most readily, which are easily liquefied by pressure, that is highly soluble. And so not only will the molecules that are highly soluble penetrate more effectively through these polymers. So high solubility in these types of polymers, like the natural rubber Graham was dealing with and silicone rubber, high solubility of gases contributes very strongly to high permeability, and permeability often goes up with gas solubility. That's not true in all polymers, and we'll learn the exceptions as we go along, but this ties in very nicely to Graham's findings. He found through his studies that increasing temperature led to greater permeabilities, even though the gas solubility decreased with increasing temperature. So this comes back to a notion of the solution diffusion model. That is that as the temperature goes up, all the gases are less soluble, but the film becomes more and more permeable to gases as temperature goes up. And this can only mean within the context of the solution diffusion model that the gas solubility must be increasing with temperature. The permeability, which includes both of those, reflects the trade-off in those two trends. And we see that very often in the literature and in the experimental work today. And it was first observed a long time ago. And so these are, as an indication of that, this is methane and butane solubility as an example in silicone rubber as a function of temperature. And as the temperature goes up, methane solubility comes down, butane solubility comes down quite a bit. So this is entirely in accord with Graham's conjecture and observation. High temperature promotes low gas solubility, and nevertheless, gas permeability often increases with temperature, and so this must reflect that the diffusion coefficients are increasing with temperature much faster than the solubility is decreasing. And we'll show that that's the case in practical situations later. This is just showing that the diffusion coefficients again in polydimethyl siloxane, this is methane, for example, that these do in fact increase with increasing temperature. So diffusion is faster as temperature increases. And finally, Graham also noted in this same paper, now this is it's an amazing piece of work, that rubbery membranes can be used to separate gases. And so this device is a Springle tube, and so he has a bag, and this is about the size of a saddle bag that he has coated with India rubber, so coated with natural rubber to seal it. And he's connected one end of it into this device and puts mercury in the top of this device. And when the mercury flows down, by a siphoning effect, it pulls the air out of this bag. And if you read this paper, it's interesting because he goes on at length to describe how to seal such a device, and it just reminds me of the troubles we have in the laboratory with getting rid of leaks. And Graham was also having problems with leaks more than a century ago. But what he found was that after he had taken all of the air out of this bag by circulating mercury through the Springle tube, he found that the tube would again start to permeate air in a slow but exceedingly regular manner. That is, that you remove all the air, and then there's more air in here that can be removed. And so he found that his bag was not quote-unquote airtight, but that air continued to go into that bag and was then removed by this Springle tube device. And he noted that this what he called dialyzed air, which is the air that has been transmitted through the walls of this bag, had 38, 40, and 41.2% oxygen. Now, air typically has about 21% oxygen, but the air that he collected that had been transmitted through this natural rubber membrane was about twice as high in oxygen as breathing air. And he noted that it would rekindle glowing wood, and that this was an example that illustrates the direct separation of oxygen gas from atmospheric air. Oxygen is more permeable than nitrogen by about a factor of 2, at least, in any polymer. And Graham was observing this phenomena. That is, he put the interior of his bag under vacuum and had air outside at 1 atmosphere, that would bring about permeation of air gases across the wall of that bag, and the oxygen would be more permeable than nitrogen, and so the gas mixture that forms inside that bag would be rich in oxygen, almost a factor of 2 higher than in air. And this has gone on to become really big business for Air Products, for example, selling gas separation membranes, not necessarily to make an oxygen-enriched air, but to remove the oxygen from air to make nitrogen-enriched air for blanketing and inerting applications. And I mentioned last time the onboard membranes to inert fuel tanks in aircraft. And so Graham goes on to hypothesize that his polymer-coated bags are not really truly impenetrable or impermeable, and he talks about it in terms of diffusion and the potential solution of the gases into the rubber, and then their diffusion and evaporation on the downstream side. It's absolutely remarkable, observation. And this is the experiment that we'll do in class. Graham observed that if he took a balloon and filled it with pure nitrogen and put it out in air, that the balloon was found to become further distended, that it'll swell after a few hours in the consequence of more oxygen entering from the atmosphere than of nitrogen escaping from the balloon during the same time. And this would continue until the composition of gas inside and outside the balloon would be equalized, and after that the nitrogen-filled balloon would shrink. And he also noted that a balloon filled with pure oxygen would simply deflate at all times during this experiment. And so we'll do that experiment in class and connect your experience here back up with that in Graham. And so with that, we'll finish the second set of notes, and we'll end the second lecture. Thank you.